I'll do it in red, okay? Cosine squared theta over cosine squared is what?
Whoa.
Cosine squared theta over cosine squared theta is
Oh,
1.
no.
Sine squared over cosine squared is squared theta, of course, because it's squared, equals 1 over cosine squared theta, which is reciprocal. Secant. Oh, I only had to memorize one. I don't have these memorized. You shouldn't have to either. Memorize this one. And if you don't memorize that one and you like Pythagorean theorem, just plug in the things, right? That's our x squared, that's our y squared. Equals our c squared, or r squared, or however you want to label it, right? 1. You know Pythagorean theorem. Plug in cosine for x and sine for y. That's all I got. These two you can figure out just by dividing. Do some quick algebra, got them. Or you can memorize it. But if you're not sure, you need a fail-safe. Your fail-safe is divide and do good algebra, right? If you don't do good algebra, well, you're in trouble. But otherwise, look, we just derived those. That's nice. Now we have those. And remember, we can move things around. So I had 1 plus tangent squared theta equals secant. Am I right? Secant? Yes. And I can figure that out if I forget it, right? We just did that. Move things around. It's an equation. Let's get tangent squared theta on its own. Subtract 1. This is also true. Why didn't they write this as an identity? Because they basically already have it up there, right? They expect you to be able to do some algebra and move things around. This is nice and pretty. This is a little less so, because you can't just divide and get stuff like we did last time. But you can move it. Let's get 1 by itself. Subtract tangent squared from both sides, right? Secant squared theta minus tangent squared theta. So if you see something like that, you can substitute 1. That's kind of cool. That's all these things mean.
Does it matter, like, the cosine and sine, the Pythagorean ID doesn't matter?
The order? No.
Because I know for, like, the rest of them it does.
A squared plus b squared is the same thing as b squared plus a squared.
Okay.
Right? Okay, so that's where we get those from. The Pythagorean theorem, which is why they're called Pythagorean IDs. They're based on.
Before I accidentally do it on a test.
Let's
and
talk
I did it wrong.
about cofunctions. Do we understand what cofunctions mean?
Yes.
Okay, so you asked a question earlier of why can't they just be together? Maybe it was Maya, right? Why can't cosine and cosecant just get together? Why didn't they make it that way? Because originally they weren't thinking about reciprocals. They were thinking about cofunctions when they named them. The cofunction of sine is what? Cosine. The cofunction of sine is cosine. Right? What's the cofunction of secant?
I'm definitely watching this video.
Cosecant. What's the cofunction of tangent? Cotangent. What does that mean? What does this mean? It means
If you put the universe in a
when you've got a triangle.
Just don't put the universe in the two.
Let's call this alpha and beta, okay? It's okay. It's just 2 different angles. 2 different angles. Right triangle. This means that the sine of this angle, so sine of alpha, is going to be equal to the cosine of beta. Alpha, beta. You guys are missing it because you're talking.
Okay.
Alpha, beta, 2 different angles. Why they're called cofunctions is because the sine of one angle is going to be equal to the cosine, the cofunction of the other angle. They're coangles. They work together to complete the triangle. They're coangles, so cofunctions. They're equal. Sine of alpha is equal to cosine of beta. The sine of alpha is the opposite over the hypotenuse. So, the cosine of beta is the adjacent over the hypotenuse. Notice they're going to be the same number. They're equal. Cosine and sine of the 2 coangles are going to be equal. That's what that is saying over there. The rule here is sine of pi over 2 minus theta equals cosine of theta. All that's saying is that the sine of 90 degrees minus whatever your angle is going to equal the cosine of that angle. That makes sense. When we have a triangle, we have 180 degrees total.
Okay.
Subtract 90 to see what's left over, because this is 90 degrees, right? So we're left with 90. So if this guy's 45, if our theta is 45, what's this guy going to be? Well, it's going to be 90 minus 45, 45. It's going to be 90 minus 45, 45. What if it's 30? I'm just making up numbers. Well, then this one's going to be 90 minus 30, which is 60. That's all it's saying. That's all it's saying. And so the sine of this guy, right? Oh, I'm sorry. Sine of this guy, sine of 60, is going to be equal to the cosine of 30.
Wait,
I lost you. Okay.
No, you're good. But like with the pi over 2.
Pi over 2 equals 90 degrees.
Okay, that's all I needed to know.
Why does it equal 90 degrees? Draw your thing.
Thing.
Pi over 2. That's a 90-degree angle.
Okay. Just that. Now you have me. You're good.
Got it. Because pi is 180, right? Degrees. I changed it to degrees because you guys like degrees better. The real theorem, or the real identity is this. Okay? That's all that's saying. Let's talk about our other identities. Let's talk about odd, even IDs. Odd functions look like this. Why do odd functions look like this? Because the original odd function, okay, the godfather of all odd functions, these are odd, okay, was this function. The function of x equals x cubed. Notice how the power is odd. If I put x to the 5th, it would get you the same looking graph. Same thing with x to the 7th, because they're odd functions. They do this thing. What's cool about the shape? Well, if you rotate it about the origin, it maps onto itself. Rotates about origin. Let's do even functions. The original even function you can probably guess. What was the original even function?
X squared.
X squared. Notice it's even. X to the 4th would get you the same dumb graph. Here's the dumb graph of x squared. If I did x to the 4th, it'd also look like a parabola. X to the 6th would also get you a parabola.
I tried it. X to 100 is
Still does, right? Even. This is an even graph. Why is it even? It's not because these are even and odd, because there are other graphs that also fall in this category that don't have powers, okay? But the original ones did. That's why they call it even and odd. The power of an even, I shouldn't say power. The magical characteristic of an even graph is that it is reflectable across the y-axis. And it maps onto itself. So any graph that reflects across the y-axis is by definition an even function, even if it doesn't have a power. An example of an even function that doesn't have a power? Great question. I'll write it in blue, because blue is even in my brain. Cosine of x is an even function. Its reciprocal is also an even function. What's the reciprocal of cosine?
1 over secant.
Just secant of x, right? Do you understand why? Yeah, okay. Because then it would be the exact same graph. We want different graphs, but we want it to have the same property. Okay. This guy, odd functions are sine of x, and its reciprocal, secant, cosecant. So cosecant x also works. And tangent of x is also odd, and its reciprocal, cotangent. Tangent and cotangent are like that couple that's always together in the hallways, right? They're reciprocals of each other. They're also cofunctions of each other. They're gross. They're disgusting. You want to punch them in the face, right?
Oh, yeah, I know.
They're always together. Always. All right. These are even. These are odd. Why? Well, let's graph sine of x real quick. Sine of x looks like this. Notice that it has that special property. You can rotate it about the origin onto itself. That's why it's odd. Same thing when we graph tangent of x. Tangent of x looks like this, right? I'll get their attention now. Tangent of x looks like this. You can rotate it, because it looks just like that, doesn't it? You can rotate it. And of course, there's lots of them. But they can all be rotated.
Do it. Do the thing.
Right, the Squidward?
No, Squidward's like this.
Yeah, he does. That's the sine graph.
Is it sine or is it cosine?
Well, it depends. If he starts low, like this, then it's sine. But if he goes high, it's cosine, right?
Okay. I'll look it up and I'll tell you.
Okay? Now I feel like in sync, but you guys don't know that, right?
No, wait.
Oh my god.
Okay,
or you're like the scarecrow in Wizards of Oz.
I love the
Where's
Scarecrow. He's my
everyone?
favorite. All right, so notice how they're odd. Even though they don't have an odd power, right? This is sine and tangent. There's no power in sight. they have this property where you can rotate it about the origin and reflect onto, or sorry, map onto itself. Let's map cosine, or let's draw cosine. The function of cosine is going to be this guy. Starts high, it's the squid, right? Notice how it's reflectable across the y-axis. Is it rotatable? No, it's not. This will end up down there. That does not map. It is even. It has this property to be able to reflect across the y-axis, which is why it's an even function. Okay. Now we got that out of the way. I hope you got this, because this is only like the third time I've taught you this. Okay. Now we can talk about odd-even identities. What are our odd functions? I'll write it in red. Which ones are our odd functions?
Sine.
And it's reciprocal, which is?
Cosecant. Tangent. Cotangent.
Just said that, ladies. I'm getting salty. Raising up the kids say now? Evens. Those youngins. Our even functions are what?
Cosine and
It's a reciprocal.
secant.
Secant.
I meant it's so
Because our even functions reflect across the y-axis, okay? Again, I'm going to draw them over here. Here's cosecant, or I'm sorry, cosine. It has this special property. When you take a negative or a positive, it gives you the same y value. Notice, this is our x value, right? Positive pi over 2, it puts out the same y value. Negative pi over 2 puts out the same y value.
Oh, squid has eyes.
Okay? Remember we do the hat? Yeah, again, third time I'm teaching you this, right?